So one thing that can be a little bit confusing is when you're writing your equation for power, do you use P equals IV or do you use P equals negative IV? And similarly for Ohm's law, do you use V equals IR or do you use V equals negative IR? And of course there's some sign convention here that we really need to be aware of in order to get this right. And so instead of sort of just writing down the rules and kind of showing you them as sort of these arbitrary things, I want to run through the intuition behind this or the thinking behind this so that hopefully it becomes a little less mysterious to you all. So first of all, we're going to talk about power. And so with regard to power, the really critical point here is that we have a thing called the passive sign convention. And so the passive sign convention is the reason why we choose the positive sign or the negative sign. So the passive sign convention says that power at a passive element, and so an example of a passive element would be a resistor, e.g. resistor. So the power at a passive element is positive. Basically says we'll use a positive sign for the passive elements. Usually we have more passive elements in our circuit than elements that inject power, so this kind of makes sense from that perspective. But this is an arbitrary convention. This is the one that you kind of have to remember as the fundamental starting point. So the power at a passive element is positive. And therefore, what that implies is that the power at a supply, something that is injecting energy into the circuit, is negative. So that's the rule, okay? And that's the one that you have to remember. If you're injecting power, we define that to be negative. If you're using power, we define that to be positive. That's the arbitrary choice. Everything else follows from this. So in order to kind of build this intuition, we're going to analyze basically the simplest possible circuit. And the simplest possible circuit is where we have one power supply and one passive element. And we just wire them up. And so in this circuit, we can get a fair bit of understanding just by thinking of our intuition when we analyze this circuit. So in particular, there'll be a certain voltage associated with this power supply, and there will be a current that will flow through the circuit. And in particular, I can draw that current in any location around this circuit, and this current is the same everywhere. So that's kind of a fundamental principle that we need to understand. The current in a circuit, in a loop like this, the current is the same everywhere in that loop. Now, the way that we would analyze this component, we know that this is the power supply, right? That's obvious. If we think about what's happening in this circuit, where does the energy come from, right? The energy comes from the power supply. Therefore, we know that the power at that element must be negative. That's the passive sign convention. So we know that the power at the source is negative. Now, when I drew the current in this way, I deliberately chose to draw this arrow as going in a clockwise direction around this loop. And I draw it in a clockwise direction because conventional current is defined to flow from positive to negative. So we know the power in the source is negative. We know current flows from positive to negative terminals of a supply. This is the definition of conventional current. It flows from a more positive voltage to a less positive voltage. And so therefore we know in this particular circuit that we have the value of I, like the numerical value of I, should be positive. So basically, therefore, here, the value of I, as I've drawn it, is positive, because that is the true direction in which the current will flow. If I had drawn the arrow the other way, it would be negative, but I know that it needs to be positive just based on the definition of conventional current. So that tells me that I is positive. By the way, in doing this, I'm assuming here that the voltage, assume voltage is positive as well. If the voltage is negative, then of course the current will swap the other direction. But I'm assuming for a positive voltage on the power supply, the current will be positive in the direction that I've drawn it. That's the definition of conventional current. So now I can think to myself, so think over here, power is negative, okay, V is positive, and I is positive. So with all of that in mind, I can write down that the correct power equation for this circuit must be negative VI. And I can reach this argument just by knowing that the power has to be negative, but my voltage and my current are positive. The only way for that to work out is if I put a negative sign there for power. So this is P is negative VI. The other way that we could look at that, and the way that I spoke about in previous videos, is that you use the negative sign because the current enters the negative terminal. Right, so if I draw that arrow, I'll draw another one here at the bottom to make this super clear. So you see this I, which goes all the way around this circuit in a clockwise direction. This current I enters the negative terminal, hence I use a negative sign for power. But if that rule feels kind of arbitrary, then what you can do is sketch this simplest possible circuit, like on the rough working paper next to you. You can sketch this circuit, and then you can really quickly think to yourself, okay, current goes this way, therefore, in order to get P as negative VI, that's a negative number, I need a negative sign. And you can just quickly think through this in your head, in case you ever forget what these arbitrary rules are. Because the fundamental principle that you really need to know is this idea in the passive sign convention that power will be negative at a supply. As long as you remember that, the rest of it you can just figure out in 10 seconds by drawing this circuit and thinking about it. So that's the answer there for power. So we can go through and kind of draw all of the combinations for that that supply. So I can have a voltage like this and a current going upwards. So that's the one that we just looked at. I can have the same voltage but the current going downwards. So I'll just label these I and V. I can also have the currents, the voltages swapped the other way around. Current going up, voltage V, and I can also have current coming downwards. So the rule here, basically we use a negative sign if the current enters the negative terminal. So let's go through and write down what our equations will be. Here, it's negative IV because the current enters the negative terminal. Here, it's positive VI or IV. I'll write IV for consistency because it enters the positive terminal. Here, enters the positive terminal, so positive sign. Here, enters the negative terminal, so negative sign. And again, if you don't want to kind of memorize this rule about current entering positive or negative terminals, then just take one of your examples and draw the circuit and see kind of which way around the current is actually going to flow. So as an example, let's take like this one here, right? And I'll draw that in a circuit and we'll develop some intuition for the behavior of that system. So I had voltages connected with the negative to the top and then that runs through some load, and I had a current I that was defined as going this way. And so I look at this circuit and I think to myself, well, which way does the current actually flow? Well, the current actually flows from positive to negative. So the actual current is flowing the other way. And so I look at that and I think, well, therefore, what's labeled here as I is actually negative. So I already have a negative sign, right? I don't need another one. I already have a negative sign. Therefore, P equals VI is negative already. No extra negative sign needed. So P is VI is negative, and that's the correct expression for the power that I should use. So here's how you can kind of figure it out from first principles. And this works for passive elements as well. So it's the same kind of argument. Let's have a look at this circuit from the perspective of the resistor. So looking here at the resistor, from its perspective, what's actually going on? Well, there's going to be a voltage across that resistor, and I know that the voltage across any node is the same everywhere in that node. So I know that I will have the exact same voltage V connected like this, and that's because this node is the same as this node on the power supply. So because they're all connected together, that's the same voltage. And similarly over here, so the same voltage and the same polarity on both sides of this circuit because those nodes are just shorted together. So that's the direction of positive voltage across that resistor. But then I had my current was defined as flowing, if I kind of continue it around, it goes this way and then it comes down here. So my current is defined as entering this way. And so I think from my, current is entering the negative terminal. And so I will get here like a different behavior. So you see on the left-hand side, it's the current enters the positive terminal. So here, current enters positive terminal of that voltage, whereas over with respect to the resistor, for the resistor, current enters the negative terminal. Okay, so therefore I need to use P equals minus VI. And sanity check here, right? I know that this final answer should be positive. So thinking power at a passive element is positive, but I is negative. So how can I get a positive answer with a negative current? Well, I need a minus sign. So therefore, I need a minus sign in P equals minus VI in order to get a positive value for power, even though my current is defined to be negative. So that's kind of thinking it through the logic for why these minus signs, that the rule works out to be the way it is. Now the other place where we have to be really careful about positive and negative signs is when we write V equals IR, right, which is Ohm's law. And so here it's really helpful to think about just the simple case of a resistor. So you have a resistor in a circuit. Now, by kind of rules of conventional current, we know that current flows positive to negative. So this, what I've just drawn on the screen, is your normal mental picture for what's supposed to happen inside of a resistor. In this case here, if V is positive, then I is also positive. because of the definition of conventional current. It flows from positive to negative. So if V is positive, then I is positive, then, well, this is nice. V equals IR. Okay, positive number, resistance is positive. All terms are positive. This is good. So V equals IR with a plus sign for this case. However, if I had drawn my currents in a different way around, so let's say I had voltage here, but when whoever labeled the circuit diagram labeled it with the current going in the other direction. So here you've got to think to yourself, okay, this is a little bit strange. Here we have drawn current as flowing from negative to positive. So thinking here, we have drawn current from negative to positive. But you think to yourself, that's not what current does. Current doesn't work like that. Current goes the other way. Therefore, the only way that this combination is mathematically coherent is the following: that if V is positive, then I is negative. It has to be. Otherwise, this is not a resistor, right? Resistors obey Ohm's law. Ohm's law says that V equals IR in the direction of kind of normal conventional current flow. So the only way that this works is if the I value is negative. So therefore, for this circuit, if I write, V equals IR here without any negative sign, then I think to myself, okay, this one here is positive. This one here is negative, and I've got a problem. Because negative resistance, right? Solve for resistance. Solve for R and get a negative number. Get a negative number, and that's a problem because that can't happen. Resistances are always positive. Not possible. So therefore, when I write Ohm's law for this circuit or this element, I must put a minus sign, minus IR, and that is necessary in order to get a coherent and mathematically sensible description of what's happening. Resistance is positive. Resistance is always positive, so you can check your analysis in this way. So the summary for this, for how to assign signs for Ohm's law, summary, resistance is always positive. Okay, assign a negative sign only if needed to make R positive. So let's draw all of the combinations. Let's have a look. So I can have a resistor, positive, negative, and I can draw a current like this. I can have resistor, again, voltage the same way around, but I can draw the current going the other way. I can have resistor with the positive, negative voltages with a negative at the top. And I can have also this situation with the current going up and the negative sign of voltage at the top. And let's look at, these are the four combinations. Let's look at how we would assign Ohm's law. So I look at the first one and I see current flows from positive to negative, and I think that's good, that's normal, that's what it does. V equals IR. I look at the next one and I see current flowing from negative to positive. Well, that's not right, that's back to front. Therefore, the correct expression here is negative IR. I look at the next example, current flows from negative to positive. That's backwards, so it should be negative IR. And in the last one, V flows from positive to negative. That's what current does. V equals IR. So that's how I figure out the sign in order to use Ohm's law correctly. And again, you can kind of get this just from your physical intuition about, well, conventional current always flows positive to negative and resistance is always positive. Therefore, from that, just a little bit of thinking, you can easily write down the correct form for Ohm's law.